Okay, then let's continue with our sessions. So we still have two talks by myself, Stefan Kiebel, and by Peter Ritter. And now this will be a talk about using some of the concepts that Christoph and Rosalind have been talking about, Bayesian inference and the Bayesian hypothesis and predictive coding. But I will apply these to perceptual decision-making, which has been established as an experimental field in neuroscience for the last 30 years. So what we have heard before is that we have models of neuronal dynamics. Then Christoph mostly talked about how you can actually analyze in a model-based fashion fMRI data. And Rosalind has been talking about EEG and more generally about electrophysiological data. And now a question to you. There is one important modality missing. We had fMRI, we had EEG and electrophysiology, and there's of course a third modality in cognitive neuroscience that is very important. Which one is that? Behavior, exactly. So we're still missing out on behavior. And why is behavior important? Because actually behavior has been used a long time. There's established theories. What I'm going to talk about is that when we look at perceptual decision-making, and I will use 3 or 4 slides to bring everyone up on the same page, what the current results are, or the core results, and then I will describe the standard model, the so-called drift diffusion model, which has been established exactly for modeling these data. And this model, and this is important now, is not a predictive coding model, but it's very useful for modeling these data. So what I'm going to propose is that we take this very established drift diffusion model and translate it to a Bayesian version using exactly the framework that Christoph and Rosalind have been talking about. And let's then see what are the advantages. We can do model comparison. I will present some of the results here. And then the summary will be very simple. So the experiments are as follows. This is a usual slide, and you find this in lots of review papers, and there's one outstanding review by Gold and Shedlin in 2007. And the idea is that you have the question, okay, how does it work that we see something in our visual field, and in a very short time, milliseconds, hundreds of milliseconds, these experiments, we can decide what we see, or we can make decisions on the input, on the perceived sensory input. And the idea is usually the same, like this. And this is now a monkey. It can be humans as well. With humans, you would, of course, not use electrophysiology, but fMRI or EEG or behavior. And you would present a stimulus like this. This is a so-called random dot motion stimulus. I will show in a second what this is. And the monkey doesn't use button presses, but he uses saccades. And once he does saccades, there's receptive fields, and these receptive fields, they're neurons, and some of these neurons are measured by the experimenter. So in other words, what the experimenter measure is not only the behavioral decision of the monkey, looking, for example, at this point, saying the dots move to the right or to the left target, the dots move to the left. This is a behavioral decision, but the experimenter can also model spikes of neurons in that receptive field. And people are looking at the activity of the neurons when the monkey is perceiving the stimulus and makes a decision. So the stimuli, they look like this. This is, I'm not sure whether you can see this, but there are lots of dots, and they're moving to the right. This is so-called 100% coherence stimulus, meaning that 100% of these dots were moving to the right. And this is a very simple difficulty level. And you can make it more difficult, and this is 30% coherence, so you see 30% of the dots moving to the right. I'm not sure whether you can all see this, but now this is a 5% coherence, and this is really difficult. So usually performance rates with this stimulus are something like 60 and 70%, no more. So in 60 or 70% of these trials, where only 5% of the dots are moving, for example, to the right, you actually get the correct response. So this is behavior modeled, behavior measured on these data. So here we have a couple of difficulty levels, which is coherence, so percent coherence like I showed before. And as I said, low levels of coherence is a difficult task level, and high levels of coherence, so many dots move at the same time in one direction, is the easy task. And what you see, and this is absolutely expected, of course, if it were different, the experiment would have gone wrong. Behavior follows like this. When the task is easy, meaning on the right, then you have 100% performance in this task with these data, for example. And when the task is easy, you have low mean reaction times. If the task is more difficult, you have high mean reaction times and very low task performance. So everything is expected. Then there are neuronal findings, electrophysiological findings, and these are firing rate traces. And important here is that these firing rate traces have been, this is from a monkey, for example, have been measured over thousands of trials. It's not unusual that a monkey makes 9,000 trials of the task I just presented, and then all these trials go into the average. So what you're looking at is highly reduced data. And usually the results come in with two areas. There is area MT, which seems to, in the monkey, seems to perform movement detection. So what you have in dependence on the motion strength, differently colored, you have high or lower activation firing rate. So, but this important thing is that it's constant over time. This is milliseconds, 800 milliseconds, so that's the time needed for the monkeys to do this task, also for humans. So the stimulus is made noisy to have long integration times or long viewing times of the stimuli to look at these neuronal traces. And then you have here this area LIP, lateral intraparietal cortex, and you have also traces, but there are now slopes on the traces, and they rise with different slopes depending on the motion strength. So if the task is easy, the rise is very steep, otherwise it's lower. So this is neuronal findings. And then at the time point of decision, so this was from the start of the stimulus, 0 milliseconds, and this is at the time of decision, which can be, of course, different in different trials. But if you then overlay all these trials, what people find, researchers find, is that whatever the coherence level, the task difficulty, the firing rate is roughly the same when the monkey makes a decision. So here is, for example, the saccade, and this is roughly the firing rate, very high, and it's the same for all coherences. These are the findings. And what has been postulated, and this is a network graph that has never been published like this, but we took the verbal description from a paper by Churchland et al. In 2008 and constructed this network graph, replicating what the verbal theory says. So the idea about this is that there is a stimulus, this is a noisy dot motion, then you have an area MT, which has two populations, left and right, and they extract the motion strength from the stimulus. Then there is a differentiator, so there's a difference taken between the neural activity here, and then there is a sign for an integrator, meaning that there's an area, for example, an LIP, which is doing nothing else than integrating the evidence, either more towards the left or towards the right. And notice that this is a feed-forward model only. So all the information comes from the stimulus, feed-forward, and at some point an area looks at the data and says left or right. That's the idea of this model. So that's a standard model. And how do you model this? Usually this is done with the drift diffusion model. And also a very quick introduction if you don't know this model. So this has been published. This is a so-called extended drift diffusion model. I won't go into the details. But the interesting thing from my point of view is that this has been published by Radcliffe in 1978. And I think there are a couple of people in this room who were not on this world in 78. So that means it's a very old model. So there are some people who were born before, apparently. Michael Breakspear is one of them, in 78. And that means this model is really 35 years plus old. And it means this model must be very useful. Otherwise, it would have been discarded long ago. On the other hand, when I see this as a modeler, it means, hey, 78, they didn't have computers then. Maybe we can do better today. So it's a strong incentive, maybe, to improve the model. So that's what we did. And what I'm going to show you now is just the drift diffusion model as it's formulated in classical terms. So what you have, it's a very simple model. It wants to model one single trial, the RT, the reaction time, and the choice. So there is a two alternative choice task, left or right motion. So what we need is two alternatives. One is here. This is so-called threshold. This is another threshold, B and B minus B. And this is 0. So what you do is just dynamics. You start a state at 0. And there are two terms then. One is the drift term, which is indicated by the red line. And one is a noise term. And that makes the red line noisy and gives you the blue time. And what it means, you can also express this as equations. So this is a continuous version. And this is a discrete version. I won't go into the equations, but what this equation, for example, just says. There are two terms. One is deterministic. It has a drift going like this. And we want, of course, to model a whole reaction time histogram, like people have different reaction times each single trial. How do we get this? By the noise on the red line. So we get a distribution. If we run this trace a couple of times, because there's always different noise on it, it hits on different reaction times. This is time, reaction times on this threshold. And of course, we can also go into the other direction, and this means that we have a trace going this way and hitting this boundary, which would be counted as a choice for the other alternative. So that's a drift diffusion model. It's just a simple model for reaction time and choice. And how it's used is that you want the noise to explain the variance in reaction time measured in the participants. And the noise is actually what can cause errors. Because, for example, imagine you have a drift term like this, but for some freak reason, there is so much blue noise on there that it goes all the wrong way to here. And that would be a decision, an incorrect decision, for example, but just because of the noise. The drift term would have ended up the trial here, but the noise drove it this way. So that's how drift diffusion modelers model principally error. So the idea how you model data is like this, that you run a trace using that model with certain parameters, and then you run it again. And what you see emerging is that all these traces, green means hitting this threshold, red means hitting this threshold, black means timeout, so like a subject actually not pressing the button within, for example, 1.5 seconds. And then you can actually run this a lot of times. And what you get is nice reaction time histograms. So you have a distribution that actually looks like what you measure with participants. So when they do, for example, 2,000 trials, which will take them, say, 2 hours, you have a histogram in the end. And you can just count how many, what you can actually compute behavior from that. So that's a model that can compute average behavior. You can compute the performance, which is just a proportion of the green correct thingies against all trials. Or you can actually measure just the mean reaction time, which is, for example, for the correct trials around here. So it's a model for emulating what subjects do over many, many trials. So how this is then used is that the drift diffusion model, as I said, is from 78. So they didn't have real computers, so you would still need punch cards, for example, to program. So what you wanted to do at this time is to reduce the data. And the good way of reducing the data is either taking the mean, or you take a couple of means, and that's usually called quantiles. So in a histogram shown here, that's the same as I showed before on the other slides. For the incorrect choices, it's a histogram here. You actually define bins, and that's the quantiles. And you have 5 bins for each choice, and these are indicated by these symbols here. And then what you do is you just plot them like this. And this is a typical plot as used in the drift diffusion model papers. And you have exactly this information here. You indicate the performance rate by the y-axis, and then you just plot the the mean of the bins, both for incorrect and for correct choice. What that gives you is a reduction from a lot of data, say 800 trials, 800 RTs, actually reduced to 10 quantiles, 1 for each alternative and 1 performance measure. And that's the data that you fit to, and that's the model, or that's what the model uses as fit to parameters. So it's highly reduced data, but that is, I think, the reason why this model has been used so much, because it's simple, it's useful, and it models the mean reaction times if you reduce them like that. So what is the Bayesian version? There's no time for this. I will only show this picture. It should be clear by now what that means. No, that was a joke. So this is just an iconic picture, as Carl Friston would say. It usually says, I won't explain the equations, but take it as face value. Of course, I know that you will think, oh, this should be the same as the one equation he showed just before. It can't be. But what we found is that this is exactly what the drift diffusion model does. And we find an absolute equivalence between this model, which models actually what the participant sees, and then there's generative models, meaning it's either the left choice or the right choice or another choice, and that you combine the model the knowledge about that there are left choices and right choices, you combine with the sensory input, and what you get out is posterior probabilities, and then in this part actually make the decision. So it's absolutely the same logic as in the drift diffusion model, but expressed as a predictive coding implementation. So this is actually a prediction model, but it's doing exactly the same thing as the drift diffusion model. And of course, you can now ask, okay, what's the point? I had the nice drift diffusion model published in '78. Why would we now go to a very complex model, or apparently complex model, that does the same thing and just calls itself Bayesian? The reason is that when you do this, you're actually in this predictive coding realm, and you can actually connect to, for example, researchers like Christoph Matthijs, who talked about the same thing in fMRI, and you talk about precision and uncertainty, and it all makes sense in this framework, but it wouldn't make sense in a drift diffusion model framework. And the other reason is, of course, that as Rosalind showed, you have then access to the huge Bayesian machinery. For example, we can use Bayesian model comparison to compare models. And you may ask, okay, is there more to it? Can we do more with this? And for example, one thing that is quite interesting for the community is for the perceptual decision-making community is that the drift rate v, which is the slope of the integration, this red line I showed you in the plot, and the r here, which is the sensory uncertainty of the agent. That's the uncertainty the agent thinks is in the world. So it looks at these noisy dots, and that's a noise level the agent infers about the stimulus. It's not the real noise level in the data. The agent doesn't know this, but it's the estimate of the noise level. And what's important, what this says, is simply that the agent has to compute sensory uncertainty, even the drift diffusion model, because it's the same thing as the drift rate. So this equivalence tells you a lot about the actual problem the brain faces. It has to estimate the motion strength and the uncertainty in the stimulus to make an informed decision. So that's shown by this equivalence. So that's one thing. And the other advantage I just show you, so the model comparison. So you can ask, what kind of model can we compare? I mean, that's a drift diffusion model. What else is there as a model how we can do model perceptual decision-making data? And I'll show you. There is, for example, the idea, and this we can nicely do with our model, but can't do this with the drift diffusion model, is you can go into single trials, as opposed to modeling just the quantiles and the performance, which is just 11 values. Instead, what we propose is to use all the data, all the single trials, all the reaction times, all the choices, which are now binary, either left or right, and we can use Bayesian model comparison to compare certain things. For example, which one is a better model? I have two here. One is the usual DDM model, which, and that's actually quite funny, the model assumes that it doesn't receive sensory input, it receives noise. So the model is based on the assumption that what it sees in the environment is noise. It sounds funny, but that's how the model works. And what we said, okay, that's a strange assumption, can we improve on it? Why don't we just feed the model exactly the same input what the participant sees? So why not show the participant exactly the visual input and then see whether the model makes the same decision as the participant? And does that explain the behavior of the participant in single trials better than the standard drift diffusion model? So that's the data. It's not fMRI, it's not EEG, but it's little dots on a matrix. So it's 24 participants, and each participant did 800 trials. And you see this by this is reaction times. Each little dot, either red or blue, is one trial. Meaning, for example, a blue dot around here means participant 12, a decision to the left. And we have these data, and this is data that will be modeled. So then we do a slight change of paradigm. Instead of using random dot motion, we use single dot tracking, meaning the subject observes a white dot and has to say whether it comes from the left target or from the right target. And there's a poster actually about this on Tuesday afternoon. And this is the behavior. It follows the expectations. So when the task is very difficult, it's difficult to say where the single dot comes from. Reaction time is long and performance is low. And what we do then is to run our models, either the drift diffusion model or the exact input model. And just to show you what you get is this here. So this is, for example, an actual choice of a participant at 1,200 milliseconds. And this is, so to say, the predicted histogram of the drift diffusion model, meaning it is in these times very likely that there will be decision, and the real decision is here. And then you look at the same trial, look at the prediction by the exact input model, and it puts it here, which has a very high density of prediction. So this shows, this one single trial which shows how this model works. It just says, it places histograms such that it follows the sensory input. And then we did some model comparison. This is really standard. This is also the model comparison using dynamic causal modeling. And what we found is that the exact input model, so the model that sees exactly the same sensory input as participants, wins hands down. And this is just shown here. And then we show the same thing here using a different measure. I won't go into details here. And then we also said, okay, instead of just showing Bayesian model evidences, why not say predict what subjects do? So the idea is that you will show some sensory input to subjects. Can we predict their choice? Can we predict how long they will take for the choice? And this is some evidence, yes, we can. So you have here difficult levels. This is the expect input model, and the drift diffusion model also makes predictions which are always worse than for the other model. And here the same for reaction times. So here for the prediction what we want is a nice straight line. We don't get this with the drift diffusion model, definitely not. And a little bit more with the exact input model, where you still see that this part here should actually be up there. So there's still something to be improved about the model. And then we did another model comparison. There is a theory in the field called urgency gating, meaning that if participants know they have to respond within 2.5 seconds. If they're within, say, at 2 seconds, they know I have to make a decision within 500 milliseconds. And there is a theory saying what they do then in this situation is to press any button, and whatever, the participant doesn't wait until the threshold is, but it hits into the direction, presses the button into the direction where the state is. That's called urgency gating. And we found lots of graphs. I won't go into this. We tested 3 different models, and we found that only with the exact input model, where you model the sensory input of the participants, you find that there's actually evidence for urgency gating. And that has never been shown in humans. It has been shown in monkeys. And humans, that doesn't seem to work if you use the drift diffusion model, but you must go to a much more precise model like what we propose here. Summary. So it's a drift diffusion model as an example. It comes from a time when there was no predictive coding. So we can easily get it into the predictive coding camp. We have shown that the equations are absolutely equivalent to a very simple Bayesian model. And we found this equivalence very useful because once you have it as a Bayesian model, you can very easily extend the model, as I've shown. For example, you modeling the same sensory input that the participant sees, and then use the whole Bayesian machinery like model comparison to actually compare different theories and hypotheses about how the data were generated by the participants. And thank you. Are there any questions? Oh yeah, please, Michael, ask a question.
Your model is able to predict how the behavior is gonna be. So your model has some parameters that changes the performance of the actual model, and like the sensitivity for the stimulus, like the decision bound. How do you decide these parameters in your model?
Yeah, that's a very absolutely accurate question. So the question is, the drift diffusion model has 7 parameters, and which one are the ones that we fit? So the important point here is that in the classical drift diffusion model, people usually fix a lot of parameters, and only 2 parameters are free. And there's a lot of correlations between parameters. For example, you can imagine by lowering the threshold has roughly the same effect as playing around with the drift rate. So you're making roughly this, you make the same decision and the same reaction time by varying one of these parameters. And of course, you have to use the same constraints in this Bayesian model. And I think what we did is we had the drift rate as a free parameter, but we fixed the threshold, and that replicates what people did in the standard drift diffusion model. You can actually decide which parameters to fix or not. A much better way, I think, is to put more information in, for example, using this exact sensory input, and we found that we can then fit some parameters even more preciser than if we didn't use that information. But it's a modeling question, what parameters you would fix.
Thank you.
So, Stefan, very nice work. Now, in predictive coding, the system would be, as we saw with Christoph, forming a model of the world, and is the model that your schema is forming a model of the... I'm guessing it's not about something between consecutive trials. Mm-hmm. It's a model of the likely direction of the dots, and is that yep. Can you just explain upon that a little? And, and what is the surprise then?
Yeah, that's a nice question. So Michael was asking. So this is now a predictive coding model, but of course, if you see dots and there's dots to the left and to the right, where's really the surprise? And the interesting thing is that yes, actually there's minimum knowledge for the participants, and my speculation is that when this task was introduced in random dot motion design task in '88 by Newsom, for example, they actually designed the task exactly like this: that you had little or no prior knowledge, so that actually you could use a drift fusion model to model this. But now what we can do, using the Bayesian version of it, we can now actually put in prior knowledge, which is usually modeled in the drift diffusion model as a so-called bias parameter, which is quite phenomenological. But now we can actually put in precise knowledge about what actually the participants assumes about the data. That's one point. And that would be, for example, also the way to implement the between trials effect. That, for example, you carry some expectation from one trial to the next, which is not in this model, but can be easily put in now that we have it in the Bayesian world. Yeah?
Yeah. So my knowledge, Wang Xiaojing had constructed a conductance-based model, which is dependent on slow NMBA currents for this experiment, and he had reduced it to a Mean-field model in 2006. Do you know it? And my question is what is difference of your model compared to this model?
You mean the attractor model by X.J. Wang, or is it another model you're talking about? Sorry, I didn't catch the name of the researcher that you cited.
Because in Xiaojing Wang's model, they
X.J. Wang? Okay, maybe I don't know the Chinese pronunciation of the name. Is it his initials are X and J? Wang?
Yeah.
Okay, good. Yeah, thank you. Then I got the question. So, yeah, X.J. Wang, and I really have to learn the Chinese pronunciation of his first name. Yeah, he proposed in 2002 in the Neuron paper, he proposed a biophysically plausible model. And in 2006, he actually reduced this to a so-called attractor model, where you have a double well system, placing a state, an initial state, and then the decision is modeled by basically the state rolling into one of these basins, and because there's noise on the state, it's either to the left or to the right, and that he proposed as a biophysically plausible model. And absolutely, I mean, the attractor, I would call this an attractor model, which has many uses in computational neuroscience, not only in perceptual decision making. And between the drift diffusion model, there are differences. Both seem to integrate information, but of course, the attractor model, because of this basin, is nonlinear. So there is a lot of papers on the theoretical and practical differences between these models, but to my knowledge, there is not many really hard differences. And what we did in some other work, I didn't talk about this here, is that we took the attractor model and also did the Bayesian version from it, and found, similar to what I told you about the drift diffusion model here, that the Bayesian version is like taking a car, ripping out the engine and putting it in an engine with 3 times more powerful, and then you can actually explain more data and have actually a mechanism that is also predictive coding. So this attractor model, yes, it has a lot of similarities with what we propose here, but we formulated another model which is a Bayesian version of the attractor model, and we compare the attractor model with this version. And this paper is under review but not published yet.
More questions. More questions is about the time scale of your dynamics. How do you get the parameter value of the time constants of your dynamics diffusion?
Yeah, in the attractor model, actually Wong used timescales that replicated, I think, NMDA receptors, for example. Yeah. And what we do in our model is that we capture these effects by similar rate constants that is actually fit to the data. So, yeah, they're very tightly related, these two models, I think.
Thank you.
Okay, I think, I guess we have one more question, then we have to quickly set up Petra.
Now, thank you for a very interesting explanation. A question that I have is that this decision threshold, is that constant over subject, and also is it reasonable to assume that it's constant over time? Because if you have a subject being doing this experiment for 2 hours, then yeah, he gets maybe bored or so tired, and then it might change.
No, absolutely, and this is, I mean, absolutely, and this is another advantage of this model, that you can put in these assumptions. Now, for example, the urgency gating I show you is exactly modeling this effect, that you have actually over peristimulus time, you can, over presentation time, you actually have a different threshold. The threshold actually goes down over time. And this, for example, habituation effect or adaptation or tiredness of the subject, you can easily model by adapting, having another parameter that goes over trials and, for example, diminishes the threshold over time. And these would then be fit to data, but we haven't implemented the latter one.
Thank you.